Okay, welcome back to CE 529. So we are into week 4 now. And the way I'm counting it on your Canvas page, it's week 3, but that's okay. So week 0, and then because we had that little holiday after that, and then week 1, week 2, week 3. So basically, this is the content that we're going to cover this week is going to be sort of the last of your midterm items. So we are going to talk about car following models. And before I do that, I have something for you to kind of take care of. And then that I didn't. So now that you've done with the homework problem for this, make sure that you do this muddiest point survey. I know it says 10 a.m. today, but obviously I didn't post it earlier. So what I would very much like you to do is maybe as soon as you get to the lab, if you can fill it out so that I know which topics I need to cover a little bit more. And then we can hit those topics back again on next Tuesday when we come back and maybe do a little bit of a midterm review session for this class. Okay, so make sure you do that. And then I also made available. I haven't yet made it available. Okay, so I need to make sure that this gets unlocked right now. So let me turn this off. Okay, so this should be available on your your Canvas page. And now we are going to talk about how, so we have talked about how we are going to route the traffic into different routes. And routing situation sort of is very related to what we do even in the macro level models. You know, traffic assignment is something that we learn first in the context of traffic assignment when we are doing travel demand modeling. And a lot of travel demand modeling happens at macro scale because we are looking at 10 years, 20 years, 15 years down the line for long range planning essentially. But still, traffic assignment is very important to us because we want to know which route traffic is going to use. So what we did was we borrowed the stuff a lot from these long range models, long-term models, macro level models when we were doing the assignments. Now, the car following a lane changing model, it's sort of a different thing altogether because we never worry about this stuff when we are doing macro level models. This lane changing and car following, all of these things only come into play when you have to deal with interaction between individual users. Yeah? And these things are important because how you structure your car following models, they have a big implication for what happens when you are, when you have two cars sort of follow in one way versus the other. That has big implications of what your macro level relationships between speed and density look like, for example. You know, we talk about Green-Shields model and all of those things. They all stem from certain assumptions that we make about how users interact with each other. Okay? So what I'll do is I want to just kind of go over some of these ideas of car following model. Car following models control drivers' behavior with respect to preceding vehicle in the same lane. Following vehicle is constrained by the preceding vehicle, driving at a desired speed. If following vehicle does not actually take care of what's happening, what are the actions of the lead vehicle, that could lead to rear-end collisions. And then our assumption obviously is that the drivers are trying to prevent rear-end collisions and their behavior will be in accordance to that. Okay. The follower's action commonly specified through follower's acceleration or deceleration. So if you have the leader, we specify the location of the leader. We specify location of the leader with the term xn. Xn is the position of the leader. Xn plus 1 is the position of the follower. And this is not quite a gap. We define that because we are looking at front bumper of both vehicles. We don't call it gap between vehicles. We call it, if you take the difference, xn plus 1 minus xn, or xn minus xn plus 1, if you take that differential, we call that headway, not gap. For gap, if you want to define the gap will be defined from this point, the rear end of the car. But when you're talking about the front bumper of both vehicles, at that point, you are referring to it as the space headway. Space headway. And space headway in this case will be defined as xn minus xn plus 1. And this distance between the two cars has a very important role to play how the follower is going to behave. And I hope that makes sense to you, because think about your experience as a driver or even a bicycle rider on a trail that's following another bicyclist, or as a driver when you're following another car on the road. If you are way behind another car, if you're way behind the lead vehicle, then you're not as worried about, what the leader is doing. You don't have to be, because the distance between you and the leader is too large. But you have to be very sensitive to their acceleration and deceleration choices if, in fact, they are very close to you. So as this headway reduces, the follower becomes more sensitive to what the leader is doing. Does that make sense? Yeah. Right. So that's the idea. So we look at this value, and then we sort of start thinking about, okay, at different levels of these space headway values, what's going to be the behavior between the leader and the follower. So look at this one. Car following models, there are 3 different regimes of car following model. One we call the free driving. So free driving would be when the gap is too large. Then the follower can do whatever they want. They don't have to necessarily care about what the leader is doing. Okay, normal following, which is you're close to the leader. So now you have to make sure that you are accelerating or decelerating in accordance to the leader. And then the emergency deceleration point is basically when your gap is sort of too close between the leader and the follower. And now follower has to take an action to avoid collision. And that could be emergency deceleration in most cases. But you could also think about sort of swirling into a different lane as well. You could look into it in different ways. But when you're talking about car following models in VSIM, we're always talking about emergency deceleration or any other microscopic simulation package, really. So we're talking about if the gap between leader and follower becomes too small and they're still moving, then the follower has to engage in what we call the emergency deceleration. So very fast, maximum possible deceleration. So there are challenges, right? When we're trying to simulate real world behavior, and this is what the point is, right? The point is to be able to simulate what happens in the real world and give some parameters to the computer so that the computer can replicate that behavior the best as it can. Because we're not ever going to capture all the real world craziness that goes on by the drivers, right? There's a lot going on in that, but our goal is to get as close to the real world as possible. So some challenges there. Driver behavior vary from driver to driver, right? And that's why. And how do we replicate that? We can't exactly replicate that, but what we do is we never assign like one value in VSIM to these things. We assign a mean value, and then we assign some kind of a deviation parameter about which that mean value can sort of oscillate between. So for example, how aggressive the drivers are going to be in following, like for example, what is going to be their reaction time? So we have a median or mean reaction time, and then every driver is assigned some deviation from that, plus or minus. In every instant, they have to react to certain things in VSIM. so that we capture that individual differences between the drivers. And then obviously, if you are talking about different context, the drivers in Los Angeles versus the driver in St. Louis, they're completely sort of different beasts because they almost have to be. So that's one thing. And then it may be necessary to use different parameters, different traffic situations. Example, if you're dealing with congested situation or you're dealing with uncongested situation. So there are different. So these are the challenges that you account for when you're trying to model the real world condition into VSIM. But that's not to say it's not possible. It's just challenging, and you might not always get, the exact replication of the behavior, but you try to get as close as possible to the real world. So there are some car following modeling approaches. We call it Gadgets, Herman Rothery GHR models, and these are also called the general car following model. And they've been out there since like 1950s, as you can see. And it's a pretty good model, really. And there are some variation of that everybody uses pretty much. Like, if you look at a lot of different simulation packages, although VSIM has we call it a different class, but these are good models. The follower's acceleration is proportional to the speed of the follower, speed difference between the follower and leader, and the space headway. So these are sort of good parameters to play with when you're trying to affect the behaviors of the users in a system, in a simulation model. And again, these notes are available on your Canvas page, so you don't necessarily have to write all of this down. Okay, so this is sort of a complicated equation, and this is something, and I should warn you that this is the math that's coming your way a little bit, at least some version of it. It's coming your way. And it looks very complicated, but it's not really that complicated, because what we are trying to say here is an of t, the acceleration of the nth vehicle at time t. So we can start writing some things down. So nth vehicle's acceleration, ant, and we can say at time t, right? So that's your left-hand side of the equation. So I should probably say LHS here. So this is the left-hand side of the equation. Is equal to, but let me first say it's proportional to, okay? So I want to say it's proportional to alpha. Alpha is a constant that makes it equal. Okay, so alpha is just a constant parameter that makes these things equal. It's some version of Vn, where Vn is velocity of the nth vehicle and then the numerator of this term is Vn minus 1 and Vn. Okay, Vn minus 1 is the leader. Okay, n minus 1 would always be the vehicle that just passed this vehicle, the same location a little bit ago. So n minus 1 refers to the leader, I should say here. N minus 1 refers to the leader, n refers to the follower. And this is sort of on purpose, because if you remember the slide I showed you a little bit ago, there I said n is the leader and n plus 1 is the follower. Okay, which is the same thing, really. You just that, you're changing a notation from n being the preceding vehicle or n plus 1 being the preceding vehicle. Okay, it's just that always the leader will have sort of a higher subscript. Okay, leader will always have a smaller subscript or lower subscript. So n minus 1 is the leader, then n will be the follower. If n plus 1 is the leader, n is the leader, then n plus 1 will be the follower. Okay? So you're basically counting vehicles as they go. So leader will always pass that point first. So if that is your nth vehicle, the follower will be n plus 1. If the leader is n minus 1, then the follower will be nth vehicle. Okay, so that's what you're trying to do. So can you tell me what this numerator is referring to? What is this Vn minus 1 minus Vn is referring to? forget the part in the smaller parentheses inside. So forget about this part right here. Forget about this part right here. But what do you think it's Vn minus 1 minus Vn refers to? Vn minus 1 minus Vn. Yes. Yes, it's exactly what it is. It's the difference in speed between the leader and the follower. Okay. And then you should probably be able to tell me what this bottom thing or the denominator refers to as well, right? It's the location. It's the spacing between the leader and the follower. Make sense? Right? So then what is this T minus T and T minus capital T doing here? What is that about? What do you think that those might be? So this, I'm going to call this top one. Oops. So I want to say something about this here. So this is numerator is speed differential. And the denominator is sort of location differential, or I should probably say space headway. And then it's not directly space headway, but some, excuse me. So bless you. Space headway, not directly space headway, but some function of space headway raised to power gamma, which could be another constant. So these alpha, beta, and gamma are three sort of parameters of the model that are constant. Okay. And then the denominator is space headway. Now this T minus T business is useful also, because what we are saying is acceleration of n at time t, and nth vehicle's acceleration at time t will be proportional to speed differential divided by the space headway. So it's going to be, so as the speed differential increases, the nth vehicle would have to accelerate more or decelerate more. Okay, depending. So it's proportional to the speed differential, but it's inversely proportional to the space headway. Right? If the gap is large, then A and T, the acceleration at time t, won't be as affected by this whole thing, by the velocity itself. So what we are saying is that the acceleration of the nth vehicle at time t will be defined by these three things: the velocity of the vehicle itself, how fast or slow you're going already, the speed differential that you've got going on, but it'll be inversely proportional to the space headway that you have. So you'll accelerate or decelerate more in response to the leader if you're close to them. But if you're far from them, you're not going to be as affected by it. And this T minus capital T, can somebody guess what that might stand for? Capital T? Not quite, not quite certain distance, but it does have, capital T also has to do with certain fixed time, but not the travel to certain distance. That'll depend on the velocity. It's a constant time that we'll assume for each agent. Any thoughts? Any other thoughts? It's a constant time assigned to each driver or agent or user, whatever you want to call it. It's a constant time. What do you think the capital T might be? Yeah. Start, no, not quite. Yes. No. So it's basic, capital T stands for the reaction time. So basically what we're saying is that your nth vehicle reaction at time t will depend on what was happening at time t minus capital T, right? Because that's the time. So their acceleration at time t will be governed by what they saw time capital T ago, right? They will see it and then they'll react to it. So capital T stands for, capital T is reaction. So if you see something right away, your acceleration is not going to change right away. If you see something, it'll take capital time t or time capital T for you to actually go ahead and apply that acceleration that you want to achieve. Yes. Yeah, so basically we are always defining. So the question is capital T always the same for n-1th vehicle or nth vehicle or whatever? But remember, we are always deriving the behavior of the follower, right? Because it's car following model. So we are just basically interested in what the follower is doing. So yes, so this is the time fixed for that follower. Okay, it could be different for different agents, and you assign that value because the leader that you've got in this sort of equation set up, that leader might also be a follower to another vehicle. So when you're trying to define that vehicle's behavior, then you'll use their reaction time. Okay? So this capital T stands for the reaction time of the follower. So I should probably specify that. And then alpha is greater than 0, and beta and gamma are also model parameters that control to what extent each of these factors affect the acceleration, deceleration of the follower. Yes. Capital T, capital T will usually be based on some kind of a distribution. So capital T will not be the same for every agent in the model. It should not be the same because that's not what it is. But then you can introduce more variability, less variability, depending upon what you've got going on in the model. Okay, so if you are looking at a mix of drivers, there's young drivers and old drivers, and you expect a lot of variation, or you expect a lot of tourists, for example, and things like that, then you could have a wider variation between capital T distributions. And then for each agent VSIM or the whatever model you're using will assign a reaction time from that, picked out from that distribution. I should probably and then there is this other class of models. The other class of models is safety distance or collision avoidance model. Okay, that's the model that you might have picked up, maybe when you're doing the driving test. What do they tell you? 1 car length between the follower and leader for every 10 miles per hour speed. Do they still tell you that? And I took the test like in 2002, so I don't know. So they still not tell. No, they don't talk about that anymore. That how much distance you should maintain when you're driving from the car that's ahead of you. So about,
I think it's like 5 car lengths.
All the time?
Yeah.
Regardless of what your speed is? They don't talk about speed anymore.
Well, yeah, I don't know.
So at 50 miles an hour, it might be 5 car lengths. Yeah, so 50 car lengths. I mean, if you're driving at 50 miles per hour, you should maintain 5 car lengths. If you're driving at 40 miles an hour, you maintain 4 car lengths. So basically every 10 mile per hour speed, you should maintain that car length. So that's a very simplistic sort of model. And you can build your whole sort of simulation around that so that, so that you are basically always at the safe distance, you have enough time to react and so forth. So this is a sort of simplistic model that some of the, maybe initially when they were building some open source models, I think even those open source models have become more sophisticated now. But this is a good rule of thumb model. If you're building a model from scratch and you want to just show some vehicles moving, this is a good model to assign to them. Is that you always keep the follower 1 car length behind the leader for every 10 miles per hour speed that they're driving. And that's sort of a very simplistic model. We call it collision avoidance model. And that's why they teach you that at the driver training for the driving test. Because most cases, this should avoid collisions. And we don't always stick to that and all that. That's another story. But this is sort of a good collision avoidance model. Simplistic, but it works. Now that brings us to the next class of models, which is the psychophysical models or action point models. Okay. Psychophysical models or action point model. It's an improved version of the GHR models. The GHR model that I showed you earlier. It's a generalization of those GHR models. So instead of saying that the same GHR models applies in all situations, the follower reacts to the action of leader even when the distance is very large. But in psychophysical models, you assign a different threshold to the speed differential, to the spacing differential. You assign certain thresholds to that, and then you assign a model for each of those threshold regimes. Okay, and then this is like an improvement of what was presented in 1958. So this has been out there since the 1960s, and the model might look like something like this. Okay, so how do we sort of visualize this model? So you see, there is delta x and delta v on the y-axis, and then delta x is on the x-axis. I mean, delta x is on the y-axis, so that's a little bit weird here, but stick with me. So on the vertical axis, you have delta x, which is the spacing, right? The headway that we talk about, headway between the two leader and the follower. So that's your delta x. Delta v is the speed differential between the leader and the follower. And then in the middle, you have what we call the zone without reaction. So you can see, if you sort of exceed a certain value of delta x, if the delta x is higher than a certain value, if delta x is higher than a certain value, let's say you're in this direction of delta x, and if you're above this point, then that's a zone without reaction. Okay? Because your gap is just too large. So at that point, the simulation model will let that whatever agent you're going travel at their free flow speed, some variation from that free flow speed, and that's it. Because remember, you assign, when you're building some microscopic models in the class earlier, you assigned a speed distribution. And that speed distribution is there to determine what speed a free vehicle would drive at. And then this is what they pick out the speed when a follower is in this situation, where the delta x is just too large that no follower has to care about what's going on with the lead. You're just too far from the lead. Then as you can see, then there is it's a two-dimensional plane here. Okay, it's a two-dimensional plane here that you could still have a zone without reaction. You could still have a zone without reaction in all these places if the delta v is small. Okay, if you are driving way slower, and then if you're driving it way slower than the leader, if your delta v is slower than the leader, you can still have a zone without reaction. And then you could see that this delta v being negative means the follower is driving slowly. Okay, follower is driving slowly. And then when delta v becomes positive, then that's when the follower is driving faster. Okay? When the follower is driving faster. If the follower is driving faster, then as the distance goes down, then you start to see, okay, this is a zone with reaction now. So you could have this whole zone. So you could see that these areas, this is a zone with reaction, this is a zone with reaction, and then this is a zone without reaction, right? So these are the three sort of areas. So what we are saying here is that if delta x is larger than a certain value, you never worry about any reaction. But when the delta x is lower than this threshold, so for example, when you're in this zone, you could still have no reaction. You could still have no reaction until there is a speed trade-off between the speed thing going on between the leader and the follower. Okay, so this is, and then again, so it's a mix of the speed and the space headway between the cars. If you are in a certain zone, you could get zone without. If you're in the zone without reaction, then your speed is not, or your acceleration decisions as a follower are not impacted by what the leader is doing. But if you are in the zone with reaction, then your things are in fact dictated by what the leader is doing. And then for each of these zones, there are different ways you pick out the acceleration, deceleration. Okay, and this is just showing like, you know, where the vehicle was. So there was a zone without reaction, and then suddenly the vehicle sort of, you know, got into the reaction zone, and then they sort of accelerated. So their, you know, delta X and delta V sort of just kind of became pretty large like that. Okay, so let's refine this. I'm show this over defined version of this for VSIM. So obviously there are no perfect car following models. There are no perfect models, but the psychophysical model that I showed you, they work really well in being able to replicate the behavior of the drivers. Okay? So let me show you what those look like. So there is Aimson is another sort of simulation model. Aimson uses like a safety distance based model. So in Gibbs car following model, vehicles are just classified as free or constrained by the vehicle in front. So you can see that the Aimson simulation package uses a much more simplistic approach to modeling the lead follower interactions. Okay, because it's using just a very simplistic model of collision avoidance. Okay, so and then there is only one threshold. You are either constrained if your delta X is small enough, or if the delta X is large, you're just free. So you're either free or constrained. And if you're constrained, then you're trying to make sure that you're following that safety distance model. And then follower can adjust his speed to obtain safe space headway compared to its leader. Okay. VSIM is a much more sophisticated approach to modeling car following. They don't reveal their secret sauce, by the way. So they don't put the model out there, like, you know, kind of like the Coke formula. They don't exactly give you what they're putting in there, but you can, you know, they have to give you what they're using. So there is so they give you that, hey, we are loosely based on this study, Wiedemann and Reiter from 1992. And then Wiedemann was like, you know, the psychophysical model that the Wiedemann proposed. And it was again published refined in Wiedemann and Reiter 1992 study. And that's what VSIM says, that PTV says that the VSIM package uses, but they don't give you the exact parameters. But that's okay. You don't have to know the exact parameters. But let me sort of talk about these things here. And again, I showed you a very simple version of this in a couple of slides ago. So this was sort of the general idea of this. But then instead of having these three zones only, you could have it like a little bit more sophisticated, which has 5 different zones. So first thing that you notice in these models is the idea of AX. Go ahead and this AX, this defines what we call the emergency region. Anytime 2 vehicles get closer than that to each other, all bets are off. The follower just has to slam on the brakes and try to stop the car. Okay, so that's the first thing that happens. Okay. Then there are CLDV and OPDV. Okay, CLDV is not something that VSIM uses, but CLDV and OPDV are sort of, you know, are basically what your acceleration is going to be defined by. So let's look at this. So these are the 3 zones: OPDV and CLDV. So CLDV and closing in, but at shorter distances. So if you look at the SDV and CLDV, the only difference between the 2 things is that one threshold applies for larger distances between the leader and the follower, and CLDV applies at shorter distance between. You can see that the CLDV curve is lower than the SDV curve, right? And you can see these, so anytime, these are boundaries of different regimes. Because if you look at, so anywhere between ABX and AX, okay, ABX and AX is, so you never want to have any distance lower than AX. So AX is basically where almost a collision has occurred. So when you are between ABX and AX, this is where the follower will try to get maximum deceleration. So anytime in VSIM, they see the distance between two cars is lower than that, then the follower will be assigned to have the maximum possible deceleration rate that's assigned in the model. Okay, so that's the region. So that's this region, okay, in between these two lines. Now, so let's say CLDV doesn't exist. If CLDV did not exist, between ABX and SDV, we call this regime what we call the closing in. Okay, we call it the closing in location. A closing in means that follower is now gaining ground on the leader and they're getting close to each other. And now they have to be really careful about what the leader does. So the acceleration behavior that's going to be in that region, it's going to be defined with certain parameters of acceleration, like sort of very closely dependent upon, and you can think of this as, you're basically keeping an eye on the brake light of the leader as a real driver. And that's what VSIM is doing too, is that it makes the follower very, very sensitive at that point. So when you're in this regime between ABX and SDV, you become sort of very sensitive. You're not exactly like, doing what the leader is doing, but you become very sensitive. You have to keep an eye out and become very sensitive to them. And then there is this region here where you're not closing in on them. You're not exactly closing in on them, but you're still close enough to them. And your gap is probably not closing, but you're so close to them, your delta X value in this region is so small that you have to react to whatever the leader is doing. So when we call it the following regime, basically we copy the behavior of the leader. So whatever the leader does, the follower also has to do, because you're so close to them. And remember the x-axis still is the speed differential. Okay, speed differential. You are basically doing, so in the following regime, you're doing exactly what the leader is doing. You're so close to them and your speed differential is so small that you are doing exactly what the leader is doing. So that's your following regime. So that's your car following, sort of, that's where the thing comes from. And then this SDX defines a distance threshold. So you can see, so some of these thresholds, for example, for this ABX and AX, these are sort of constant values. These are horizontal lines. What does that mean? That these thresholds are characterized by what? These thresholds are characterized by how far apart leader and follower. Okay? And the same thing with SDX. They are sort of horizontal thresholds. How close they are, how close the two vehicles are. And then these curved thresholds, they are not just dependent upon how close they are, but they're dependent on two things: how close they are and what is their speed differential. So what this tells me is that you could actually be close to a vehicle. You could actually be close to a vehicle. So for example, if you are talking about this regime, this OPDV threshold, you could actually be close to a vehicle, but not be in the following regime. When you're going way slower than your leader. When you're going way slower than a leader, so means so way slower regime would be here somewhere. Okay, you can be very close in terms of AX type thing. You could be very close to the leader, your delta X being very small, but because your delta V is way to the left, you're driving way slower than the leader. So you don't necessarily have to follow the leader exactly, because you're not worried about getting into collision because the leader is driving faster than you are. Okay, at that point, so you don't worry about that. So VSIM assigns a different sort of model or acceleration for the follower, depending upon where you're falling in. And then the algorithm is designed to make sure that you are accounting for that. So now, we never almost have to worry about specifically what the model is, because obviously we don't know what the model is. But knowing this is very important, because when you're building a simulation model, you will see that sometimes your cues are not discharging fast enough. And then we do this type of a calibration validation approach when we are, let's say we're modeling an intersection. And so what we do is we observe the data in the real world, and we observe the data in the simulation. And then we try to see, is our simulation model capturing the behavior correctly? And for example, we've done some models where we noticed that when we were doing a model for an intersection, the cues in the real world were being discharged very, very fast. But the cues in the in our simulation models were going out very slowly. And I think the difference was, what we found was that the problem was we had to sort of make our drivers a little bit more aggressive. And we had to lower this AX threshold, because VSIM wouldn't let drivers kind of get close to each other, more closer than each other. But in the real world, the drivers were sort of backing behind each other more closely than we were assigning them. So there are, like, thresholds that you can change. There are thresholds that you can change if you know what each of those thresholds mean. Okay? So here are some definitions that you can see. AX is the desired distance between stationary vehicles. So we never want that AX threshold to be reached. ABX is this desired minimum following distance at low speed differential. So that's your ABX. And if you're wondering what these acronyms stand for, this acronyms actually mean something. But they don't mean anything to me, because they came from the German language, because VSIM was developed in Germany. The CLDV and SDV and all these things, they are acronyms of whatever the German word for approaching point might be. Okay. And one time I looked it up and I found it, but there is no value in you learning German in this class. There is value in learning German independent of this class, but there's no value in that here. So SDX is the maximum following distance. CLDV is the decreasing speed difference. And OPDV is the increasing speed difference. Okay. So you could see, so if you look at these things, SDX, so as you exceed the SDX, then you get into the free driving mode. Okay. If you're between ABX and SDX, you're generally in the following mode, but you could be in the OPDV mode if you are to the left of this line. Okay, and this line is not just defined by delta X, as SDX and ABX and AX are defined just by delta X. OPDV is defined by the relationship between delta X and delta Y. Okay, and then OPDV, as you know, stands for increasing speed difference, and CLDV is same as SDV, but at the shorter distance. And SDV is the approaching point. CLDV is the decreasing speed difference, and decreasing speed difference at shorter distances. Okay, it's the same as SDV, but just where delta X is small. So here are some things. If you look at the base data and driving behaviors in VSIM, you'll be able to locate these things in the model. CC0 and CC1 and CC2 and all of those things. Okay, so you can see the standstill acceleration. So that was another parameter that we had to adjust when we were doing that intersection modeling, when our cues were not clearing as fast. Okay, the standstill acceleration, we just had to bump up the value, because I think newer cars, they accelerate much faster, and you wanna account for that. And then acceleration, sometimes if you're having merging issues, if you're having the vehicles merge from the ramp and they're not merging as fast, right? So then maybe this is the parameter you need to play with. It's what's the acceleration that vehicles can generate. And these are the thresholds. Following, so some of these thresholds are defined based on, based on the slope of the lines and so forth. So this is what this is: positive following threshold 0.35, negative following threshold negative 0.35. So you're basically defining two lines that are sort of like that with the exact same positive and negative slopes. And then CC0 and CC1 and CC2 are also, CC0 is your AX, basically. Emergency, like what's going to be the standstill distance between the two cars. So that's about 5 feet. CC1 is the headway time, and CC2 is the following variation. And CC2 is basically, so you can see that some of these things are defined based on just feet, 4.92 feet and 13.92 feet. So these things are these straight up, these straight lines, the horizontal lines. And then, so again, and these models, car following models, there is one model for freeway where you can do free lane selection, but there is other car following models for non-freeway situations. For arterials, the model is a little bit different because you're probably not going to accelerate as fast, things like that. Yeah? So now, because these things are so important when you're modeling things, a lot of state DOTs want to make sure that you have the tools as a modeler to be able to model this thing. So what I've done is I've made available, and this is also thanks to Dr. Amir Molan. I was just showing the Oregon DOT's VSIM manual. So some states have their own microscopic simulation manuals that they define these parameters. Okay, so for example, VSIM always has default values for all of these different parameters, right? Now, Oregon DOT says you can play around with these parameters, but always be in that 4.5 to 5.5 feet range. Okay. And if you're in the merging, if you're in the basic segments, put it that one. If you're in a merging or a weaving segment, you should always be higher than 4.92. Okay, because they think that 4.92 is too aggressive. Okay, they want that standstill distance to be a little bit larger. Okay, for their drivers. And different DOTs might have a different suggested value. And so you might always want to look up, depending upon the location that you're modeling, you might want to look up if there are some guidance that has been issued by the state DOT, maybe the city DOT, maybe city DOT. You can ask them if there is some kind of guidance that's available to play around. And then for the rest of them, because all these things are way too complicated, they don't want to mess with that. They just say like, okay, suggested and just use default value. You can still mess around with that. It's not like, you can't, but then you might have to justify why you did that. So maybe some calibration issue that you're trying to address or whatever it might be. Okay? So this is from the Oregon DOT VSIM manual. I have posted, I think, Louisiana's, and then maybe a couple of others are also posted on Canvas, just for reference. You don't have to ever worry about them necessarily for this class, but you should know what all of that means when you're trying to model these things. Okay. So desired bumper to bumper speed and then headway time, but the distance in seconds that the driver wishes to keep. So this is the desired safety distance, CC0 plus CC1. So you can sort of get at, for certain situations, you can get what the desired safety distance might be based on even these parameters that you specify in this. But obviously we know that once you pass that threshold, there is much more complicated stuff that's going on. So what I'll do is I'll stop here. We'll pick up this discussion in the next class. And I also have to sort of cover some sort of theoretical foundations of what is the relationship between the micro and the macro models. So we'll cover that in the next class also. Thank you, and I'll see you in the lab. And we'll start a new lab today.